Hello there. In this lesson, we're going to learn a little bit about some of the properties and chemical reactions that good old hydrocarbons that we learned about in the first lesson can undergo. So if you recall, our simplest molecules are called alkanes, and they are the molecules that have only single bonds between the carbons and, of course, hydrogen as well. And since carbon and hydrogen have pretty much the same electronegativity, these molecules are going to be non-polar. And the force of attraction that holds one molecule to another molecule will be what's called dispersion forces. Now, dispersion forces are those forces due to the movement of electrons not always being symmetrical around the molecule. And so that means bigger molecules will have more electrons and therefore more of this attractive force. And so bigger molecules then will have lower melting and boiling points because that force of attraction will be stronger for those. So what you do is if you have a whole mixture, like when you dig oil out of the ground or pump it out of the ground, what you do is you heat it up really hot to begin with, and a lot of those molecules will turn to a gas. And then you cool it as it rises through, it's called like a distillation tower, a fractional distillation tower. And as it cools, different sized molecules will condense and then can be collected, right? And so at the hotter temperatures, you'll get bigger molecules, like these ones used as fuel for cars. Clearly I got this graphic from British source, a lorry, a truck. And then as you go higher up and you get to the cooler fractions, smaller and smaller molecules will condense and can be collected for different things. And then the other gases that don't condense, you can just collect and bottle them at the top here. So yeah, longer chain means more dispersion forces, and that gives the higher melting and boiling point that used for this separation. So now that we got all of these different hydrocarbons separated, what can we do with them? Well, there's all sorts of reactions. We're going to look at them a piece at a time as we go through the rest of the course. But the one reaction they can all do, no matter what, is they can all burn in oxygen, right? So combustion is always an option for any of these alkanes, alkenes, alkynes, any of the other molecules they're going to get to along the way. They'll all burn with oxygen and produce carbon dioxide and water and some other products if there are other elements in there. The second reaction we're going to look at is substitution. So substitution is when you take off a hydrogen and replace it with some other element, right? So a good example of this is halogenation. Is when you replace a hydrogen with a halogen. And so what you'd end up with here, instead of having 4 hydrogens around this carbon, you'll have 3 hydrogens and a chlorine. And then you'd have the hydrogen that you pulled off and the other chlorine as a product. So you're only going to replace one at a time here, right? And if we have this molecule here and we put it into some bromine under some specific conditions, you'll end up with the same molecule, except in place of one of the hydrogens, you will put, let's use a different color, the bromine. And you'll end up with the hydrogen over here and the other bromine attached to it. So that's substitution, where you substitute the hydrogen with something else. Now the molecule you end up with when you substitute a hydrogen with a halogen, they're called alkyl halides. And alkyl halides are going to have a halogen on there, like chlorine or fluorine. And this changes the properties of the organic molecule. Fluorine especially is a lot more electronegative than carbon. And so if there's a fluorine there, that's going to make your molecule more polar and will change things like melting point and boiling point. A place where you might have heard of these molecules before are the CFCs, chlorofluorocarbons, that are found in refrigerants. And so a couple decades ago, they figured out that it was these CFCs that were causing degradation of our ozone layer. And so we use different molecules now that are less harmful to our environment. But these worked well for a long time, except they were destroying the ozone layer and we just didn't know it. So another group of molecules that can undergo the substitution reaction are called aromatic hydrocarbons. So aromatic hydrocarbons are a little different than the aliphatic ones we've looked at so far. With aliphatic hydrocarbons, the electrons that are between the carbon atoms stay put. They're always between the same two carbons. But with aromatics, they're shared. And what you have are resonance structures where the double bonds are shared between multiple carbons and equally throughout the structure. So the simplest one here is benzene, where you have 6 carbons in a loop, and it's called aromatic. They do have a unique smell to many of them. Naphthalene is one that is part of, used to make mothballs, which would repel moths from the chests where people used to store their clothes when that used to be a problem. And so what happens is that when you have an aromatic like benzene, it will be able to undergo substitution just like an alkane would. And that means substituting the place where the hydrogen is with another element or group. In this case, we're adding some bromine on here. And so you're going to substitute bromine for where one of the hydrogens are, and that hydrogen will end up going with the other bromine in the pair there. And so, yeah, another substitution on aromatic molecules which have these ring structures with the alternating double and single bonds. Now, since we brought up hydrocarbons that have multiple bonds, we should also include a term that is often used with respect to those. So saturated versus unsaturated refers to how many hydrogens are possible to be around a given hydrocarbon. So we got propane here. Propane has 3 carbons and all single bonds, and so it would have the maximum number of hydrogens possible. And when the maximum number of hydrogens possible is on a molecule, that is called saturated. It's like saturated with hydrogen. Can't get any more hydrogens on there. Now, if we draw propene, that has a double bond in it, this one is deemed to be unsaturated because it doesn't have the maximum number. The maximum number here is 8 hydrogens, right? This one here only has 6 hydrogens, so not saturated, and so that's often used as a term to group together all those molecules that have multiple bonds, because they'll all behave in similar ways due to their not being saturated. So when there's a double bond, you also have 2 options for the shape. These are called geometric isomers, and that is because double bonds can't rotate like single bonds do. And so if you have the carbons on either side of a double bond and they're on the same side as each other, like with this cis-2-butene, that's called a cis isomer. And you can kind of see it's like a letter C there, right? So a cis isomer has the carbons on the same side, and then a trans isomer would have your double bond, and then the 2 carbons that are attached would be opposite to each other, right? And we look more like this. So these are isomers, obviously. They are the same formula, but geometrically they have a different shape. So cis on the same side and trans opposite. The last thing we look at in this lesson are the addition reactions. Addition reactions work for alkenes and alkynes, but not alkanes and not those aromatics. And so when you have an alkene or an alkyne and you add in a molecule, what happens is that one of those bonds from the double bond gets broken, and then the new thing is added on. So in this case, it's called hydrogenation. We're going to add hydrogen onto either side of where this double bond is. So we're going to put one here and one here. So you end up with a single bond between the 2 carbons, and then the extra hydrogens go on either side of where the double bond was. So that is an addition reaction, subset hydrogenation. There are a whole bunch of addition reactions. They all work the same way. In this case, we have a bromine being added onto a molecule with a double bond, right? And so you're going to end up with that double bond being opened up. You got the same hydrogens that were there before, and then the bromine will go on either side. This is used as a test for saturation because bromine has this brown color. And if you do the reaction, if there's a double bond, if you got an unsaturated hydrocarbon, it'll react with the bromine and then it'll go clear, right? Because the bromine will be part of the molecule and it won't be brown anymore. So the saturation test is brown if it's saturated and clear if it's unsaturated, right? The other two here work the same way. We got a hydration reaction. This time the water molecule will split. One side will get the H, the other side will get the OH, and the other hydrogens will stay as they were. And the last one here is hydrohalogenation. And so you got hydrogen and a halogen, and it works the same way. You got the hydrogens where they were, and you stick a hydrogen on one side and the halogen on the other. So there you go, 3 more addition reactions. They all work pretty much the same way. They get fancy names, but they mean the same thing. Hydration, hydrohalogenation, halogenation, good times. The last thing we're going to look at here is what's called Markovnikov's rule. I'm not sure who Markovnikov was, but I assume a Russian chemist. But the way it works is sometimes called the rich get richer rule, and it's referring to hydrogen. And so if you look at these 2 carbons on either side of this double bond, one side has 2 hydrogens, the other side only has 1 hydrogen. So you'd say that this carbon over here is more hydrogen rich. And so what happens is the most common product of this reaction will be the carbon with the more hydrogens will get the hydrogen from the addition reaction. So you end up with all 3 of the hydrogens on this guy, and the bromine will go on the middle carbon, and the others are there as well. So that'll be the major product. Most of the product will end up going like that. It has to do with the mechanism for this reaction, which we won't go into here. You'll get a little bit of the other one, but if you're going to just put down one product, just do the major one. This would be the minor product, which would happen a much smaller percentage of the time. Right? So we'll ignore this one for now, and we'll just focus on the major product, which would be the one that follows Markovnikov's rule. All right, hope that helps. Get your practice. We'll talk to you soon.